Okay, last time we started to talk about membrane fat composition and why that's interesting. There's an enzyme called D6D or delta 6 desaturase, which, if it's converting linoleic acid to something called arachidonic acid, then in your membranes you can give off these oxalams or these oxylipins or these oxidized PUFA. And so that's important. There's a lot of action that happens in the membranes. This kind of diagram here shows this is the membrane. This is the phospholipid bilayer, if you will. This is one of the individual fats that is in this membrane. This is phosphatidylethynolamine. That's a very complicated word. When we talk about triglycerides, so this right here is a fat molecule, and it's a straight one. So that would be a saturated fat. That would be like palmitic acid or stearic acid. And these two individual fat molecules are connected to a glycerol molecule, and the glycerol molecule can basically connect three different things. So in a triglyceride, you'd have a third fat attached to this third spot on the glycerol. But in this case, we have a phosphate group, and phosphate is a charged molecule. It's polar, and things that have positive charges or negative charges like to dissolve in water, and things like fats that are very they call it non-polar, but they're neutrally charged molecules. Those are the things that wind up being fat soluble. And so what happens is, due to the positive charge here and the fact that these are neutral, the fatty molecules all align in the center, and these positive phosphate groups are on the outside, and that's how we can form these phospholipid bilayers. And these things are also sometimes known as lecithins, and lecithins are emulsifiers. You put them in food because they help bind the fatty parts and the liquid parts of the food, and that's why you see soy lecithin in things. And somewhere along the line, for whatever reason, in biology, we stick these what are called head groups onto this phosphate molecule. And there's a bunch of different head groups, but one of the most common ones is this thing called ethanolamine. And ethanolamine sounds really complicated. It's a bit less complicated than it probably sounds. This is ethanol. It's just two carbons with hydrogens and then an OH on one end. And this is an amine over here. It's really just an N, and this R means it can be stuck onto anything. So it's really just this kind of NH2, or it can also be NH3 plus if it has a third hydrogen. And so if you were to take this OH group from the ethanol and this like linear, when it's just a stick like this, whenever there's an angle, you can assume that there's a carbon and two hydrogens there. And so this is literally just ethanol amine, because this NH3 group is just stuck onto what would otherwise just be ethanol. And so ethanolamine is a scary sounding word. It's not as complicated. And what's really interesting about ethanolamine is that in 2021, this paper was published that says ethanolamine forms efficiently in space, and if delivered onto early Earth, could have contributed to the assembling and early evolution of primitive membranes. So we may really be made of space dust. That's not just a thing that your yoga teacher says. And the reason that we're interested in this ethanolamine is that these membrane phospholipids play a role in signaling, in fatty acid signaling and metabolic signaling. And you can see this article is called Regulation of Food Intake by Oleoyl Ethanolamide. So these things are similar to what they call endocannabinoids. Cannabinoids trigger your cannabinoid system. Endocannabinoids mean that we make them in the body, and so they trigger through the same pathways that THC or cannabis is signaling through. But we make them in our cell membranes, like I say, and what happens is, so you have phosphatidylcholine down here. What happens is you take a fat off the first position in phosphatidylcholine, off SN1, and you stick it onto the nitrogen in the phosphatidylethynolamine, and then it becomes this thing called NOPE or NAPE. There's another enzyme, and it cleaves this bond here where it's connected to the phosphorus, and this becomes OEA. So the oleoyl in this case means it's oleic acid, which is from olive oil, of course. And of course, we make oleic acid in our bodies via the enzyme SCD1, starting from stearic acid. And so now this thing is released from the membrane and it is just floating around in your plasma, and it is acting as a signaling molecule. And then there's another enzyme called FAAH. And what that does is just cleaves this bond, and it goes back to just being free fatty acid, oleic acid, and free floating ethanolamine. And that sounds kind of complicated, and it sort of is. And so we can actually make several different kinds of these ethanolamines, or once they're free floating, they actually become ethanolamide. So it's oleoyl ethanolamide once it's in solution. We can make a bunch of them, but the most well-known is this oleoyl ethanolamide made out of oleic acid. And you can see it is an endogenous PPAR-alpha agonist. And I've talked a lot in the past few videos about PPAR-alpha. When animals go into torpor in the winter as they're fattening up, they upregulate PPAR-alpha. So one of the things that means is when you're in torpor, by nature, you burn fat. And that's what this slide is all about. Once we activate PPAR-alpha here, you see fatty acid oxidation. You're burning more fat. So this sort of glowing review about oleoyl ethanolamide, you see it's triggering PPAR-alpha, and that's reducing oxidative stress, and it's reducing inflammation, and it's reducing non-alcoholic fatty liver disease, and it's reducing cirrhosis, and it's increasing fat oxidation. And your intestinal cells, OEA, is activating PPAR-alpha, and that is increasing satiety, and it's decreasing food intake, and it's decreasing obesity. So it sounds pretty great, right? Who doesn't want that? And in fact, we've done some studies in humans where we've given them OEA as a supplement for 60 days, and people lost about 2.6 pounds in 60 days. And that obviously is not a huge amount of weight to lose. But as a single intervention trial, this was statistically significant. This is a significant weight loss, even if not a super relevant weight loss. But that makes it kind of interesting, right? We can say people did statistically lose weight when they consumed OEA, and it also subjectively reduced people's feelings of hunger. So you can see before they started taking OEA at a certain point in the day, they take some questionnaire and their hunger is at a 7. After the OEA, that on average was a 6, and that was another statistically significant result. So it seems like it had some small effect on appetite regulation. When you look at infants, when they're talking about OEA, SEA, so that's stearoyl ethanolamine, that's made with stearic acid, and PEA, that's palmitoyl ethanolamine, that's made with palmitic acid, the 16-carbon saturated fat. It says OEA, SEA, and PEA concentrations were lower in the high compared to the low weight for their age group of infants. And a higher concentration of SEA specifically, so that's stearoyl ethanolamine, was associated with lower anthropometric measures, e.g. triceps, skin fold thickness, and weight gain per day since birth. Infants who were heavy for their age tended to be, and that's the red dots, when infants are ingesting these ethanolamides from their mothers, maybe that is having some effect in controlling their weight. There's a flip side to this. If you look at obese humans, what you actually see is that OEA levels are over here actually, and this is premenopausal and menopausal women are the two groups, and this is normal weight, overweight, and obese. And what you can see is that from normal weight to obese, OEA circulating levels actually increase in obesity. And the same thing is true for PEA. And this third one, AEA, is very interesting. This is also known as anandamide. And anandamide activates the CB1 and the CB2, which are the main cannabinoid receptors. And so these other PEA and OEA are kind of analogous to cannabinoids, and they sort of have some kind of cannabinoid function, but we don't really understand how it works. AEA actually triggers the cannabinoids, and AEA definitely increases food intake. It gives you the munchies, as they say, and AEA is definitely associated with obesity. And you can see that AEA and PEA and OEA all kind of go up together in obesity, and this is in men. This is the same chart, but this is in men. And you see again, in obesity, AEA is up, PEA is up, and OEA is up. And so OEA and PEA are both pretty widely sold as supplements. And so I want to kind of dig into why I'm actually starting to offer SEA, stearoyl ethanolamide, as a supplement. You can get it at fireinabottle.net/shop. Obviously, if you get some of this, it helps me run the blog and make these videos. This product I'm very excited about because, to my knowledge, this is not available in the US right now. And I love it when I can offer a new product that I think can help people. As you go through this video, you'll see that our knowledge about this is pretty limited. So I'm also asking you guys to be guinea pigs, give this a try. I think it is very safe. We all make SEA in our bodies every day. I don't think there's a huge safety risk here. I think it's an interesting thing to try and see what happens. This study is looking at mice. The question is, what controls the levels of this OEA and the SEA in your body, right? Because we're going to talk about it as a supplement, but of course, it's also interesting how our body is controlling these levels. So let's look at this one I have circled. So this is stearoyl ethanolamine. And the question is, when you look at plasma, you look at circulating stearoyl ethanolamine, how closely correlated is that to stearic acid, right? Which is what it's made from in different tissues. So that's what's being shown here. And in fact, this VAT is visceral adipose tissue. And so you see that SEA levels are, at least in mice, pretty closely correlated with adipose tissue levels of stearic acid. One of the reasons that this correlation is interesting, of course, is that in my talk, The History of Body Fat Composition, I showed that stearic acid levels in adipose tissue in America have actually dropped from about 8% in 1943 to around 3% on average by the 1990s. There's reason to think that people in America before the obesity epidemic had higher circulating levels of SEA than they do now. But like I say, there's not a lot of studies have been done on these molecules, not nearly as much as you'd like. So we're speculating a bit. And of course, I was interested in SEA, the steroidal version of this, partially because I knew that, and this is one of the articles that started my whole blog, Fire in a Bottle. This is an experiment where they fed mice, either this is sort of a normal low-fat chow diet, or and then they went another 10 weeks on the low-fat diet. So that's kind of your control mouse. And they fed them either oleic acid, which is, of course, would produce OEA, or they fed them stearic acid, which may, or we're not sure if consuming dietary stearic acid actually produces a surge in SEA. My thought is that it probably does. But that's not actually something that, to my knowledge, is known. But anyway, the mice who were fed the stearic acid stayed really lean, and especially compared to the ones who were fed olive oil and got fat. And so this is a little bit of why I'm interested in this conversation of SEA versus OEA. Do we do, this OEA that's being sold as a weight loss supplement? If we want to try some of these very interesting ethanolamides, is OEA the one that we really want? Let's dig first into SEA. When they give mice a dose of this SEA, this is how much food they eat over the next hour. If you give the mice sufficient SEA, it actually reduces their food consumption by about half. But interestingly, in that same study, it showed that there was a massive reduction in SCD1 in the liver due to this SEA supplementation. And so that is about a threefold reduction. And that is really huge, right? And so SCD1, of course, is the thing that converts stearic acid to oleic acid. And so what you start to see in some of these is there are some clues that OEA and SEA may actually be at odds with each other. And so I talk about this torpid metabolism. It's possible that there's one side of the aisle where you have a lot of stearic acid, you're suppressing SCD1, and you're staying in that kind of warm-blooded metabolism. But when everything flips, oleic acid levels rise, you make more OEA, and then you're in a different metabolism. But having SEA in the first place may help you suppress SCD1 and keep you in that stearic acid mode. And so in the last couple of episodes, I've talked about the SCD1 index, which is the ratio of oleic acid to stearic acid, but also the delta 60 saturase index. And that shows the activity levels of these two desaturases, SCD1 and delta 60 saturase. And those enzymes predict, if you watch the video about D6D that I just did, or the history of body fat composition, those two enzymes predict diabetes, they predict mental depression, they predict heart disease levels. If you have upregulated D6D and SCD1, there are really bad outcomes associated with that. These are control rats, and when they were given this diet that gave them insulin resistance, and you can see delta 60 saturase index nearly doubles from 0.007, we could just call it 7, and it goes to 12. But then if you give them, so this was after they were insulin resistant, they just gave them an NSE is the same thing as SEA. So they just gave them SEA for a couple of weeks, and it went back down from 12 back down to 9. So that's a pretty good result. And this is SCD1. It went from 2.9 in the controls to 3.8 when they were insulin resistant. And if you give them the SEA, it goes all the way back to 2.7. And this is SEA's effect on inflammation. I talked in the last video about how activating something called NF-kappa beta, which is like the OG transcription factor. If you activate that NF-kappa beta even just a little bit, it upregulates lipogenic enzymes. And so this study showed that with SEA, that NF-kappa beta did not go into the nucleus and turn on the genes that's its job. It's a transcription factor. It goes in the nucleus and it turns on all these genes associated with inflammation, one of which is tissue necrosis factor alpha, TNF alpha. TNF alpha is here, and then the ones that are insulin resistant, it basically triples. But if you give them SEA, it reverses that TNF alpha back to baseline levels. In the insulin resistant rats, the red bars, you see that these are the different, this is like phosphatidylcholine, this is phosphatidylethanolamine, and you can see these are all dysregulated. And in every case, I want to say, giving them the SEA starts to put those membrane fats back towards the control group. Like I say, there's not a ton of research that's been done on SEA. Most of these studies are all by the same group that's actually in the Ukraine. And that's a lot of the data that we have. There's not a ton more, but you do see effects on appetite control. You see lowered inflammation, and you see some restoration perhaps of these underlying enzyme systems involved in lipogenic enzyme expression. And so the flip side is something like OEA. Should we be eating a lot of olive oil? Should we be taking OEA supplements? Should we be doing other things that activate PPAR-alpha? Because you saw that slide in the beginning, all the great things that PPAR-alpha does, right? It increases fat oxidation, etc. And so this is from a different paper, and I just like this photo because it shows the sort of natural agonists, and that means activators of PPAR-alpha, right, is what it's talking about. And you see that OEA and PEA are on the list, but SEA is actually not. As far as we know, SEA does not activate PPAR-alpha, and so that makes it a little different. So in obesity, and I already showed this graph, OEA and PEA are both increased, but 5-HEAT, I showed this in the last talk about D6D, 5-HEAT is increased 30-fold in obesity, and 5-HEAT is also a natural activator of PPAR-alpha. And if we want to have some real fun, another thing that is a known potent activator of PPAR-alpha is oxidized frying oil. So that's when you take soybean oil and you leave it in the deep fryer for a week. Oxidized frying oil has been shown to be a PPAR-alpha activator. And in fact, if you give oxidized frying oil to rats, so you can see, so this is the control rats. After the experiment, they weigh 556 grams. These are rats that have been given oxidized frying oil. Well, these are given normal soybean oil, and they get fatter, so they're almost 600 grams. But the ones that get the oxidized frying oil actually lose weight and only weigh, they gain less weight, and they only weigh 500 grams. at the end of the experiment. So we could actually say something like oxidized frying oil has been shown to prevent weight gain in rats, which is a true statement. But I don't know that that's the route that I would choose to go down. Also, when you activate PPAR-alpha, that initiates torpor in mice. So these mice were given a bezafibrate, which is a pharmaceutical activator of PPAR-alpha. And you can see this is their body temperature. And the gray mice are on the bezafibrate. And ultimately, right, these are actual torpor bouts where their metabolism really slows down. But even before you have this bouts of torpor, the PPAR-alpha activation is already lowering their body temperature. And I like to talk about one of the big changes that we've seen in humans over the last 100 years is that we all have lower body temperatures than we used to. A good friend of mine just went to the ER the other day with shoulder problems, and when she got her temperature checked in the ER, it was 97.2. And she said that no one at the hospital even blinked. That's just a normal body temperature now these days. And that was not the case before. This is another study in mice, and they gave these mice fenofibrate, which is, again, it's a pharmaceutical activator of PPAR-alpha, just to kind of, so the question is, what happens when you really activate PPAR-alpha? Is this a thing that we want to be doing? Because, you know, it does increase fat oxidation, right? And so what they saw in these mice, you can see there's profound modification of fatty acid profile, and that is true. So you see, this is the normal mice, and these are the ones given the PPAR-alpha activator. And you can see saturated fat levels significantly drop. Monounsaturated fat levels go up by about 50%. They go from 927 up to 1400. And this omega-6, this linoleic acid level drops from 1600 down to 1300. And as I said in the last one, that sometimes is an indicator that delta-6 delta is active and that omega-6 PUFA is being converted to things like 5-HEAT. And then these are the two indexes of SCD1 activity. And so you can see this is SCD18 that I talked about in the history of body fat composition, goes from 2.5 to 5. So that doubles SCD1 activity. And this is in the liver. And then you see the SCD16. So this is palmitoleic acid over palmitic acid, also nearly doubles. And so this PPAR-alpha activator is massively increasing SCD1 activity. And so that pattern that you see, this is a study from 1968 in Germany. And so this is people that are heavier. These are over 70 kilograms, which is maybe over 150 or 160 pounds, as opposed to people who are lighter. And you see that same pattern of dropping saturated fat, increasing monounsaturated fat, and dropping linoleic acid. This is something, this 23N9, when you activate PPAR-alpha, goes from 3.6 to 20. That's what, a 5 or 6-fold increase, I think. And I've been telling you guys this whole time that animals and humans can't make polyunsaturated fat, right? They can only come from the diet. So if you don't eat polyunsaturated fat, you can actually reduce the amount of polyunsaturated fat that you have. And it turns out I've been lying the whole time, because we can, it turns out, make this thing called mead acid. And it's the reason that it's omega-9 as opposed to omega-6 or omega-3, which we get from our diet, is that we make it from oleic acid. And here's how we do that, right? So both ways. So this FADS2 is D6D, delta-6 desaturase, the thing that I keep talking about. And oleic acid is, of course, made by SCD1. And so here's the two pathways that you can make mead acid. And so they basically both involve SCD1 and D6D, the same two things that predict, diabetes risk. And so if you make a whole bunch of both of them, you end up with mead acid, which is exactly what happened in the mice who were given a PPAR-alpha activator. This is about Alzheimer's disease, and it says the analysis revealed elevations in levels of monounsaturated fats and mead acid in midfrontal cortex, temporal cortex, and hippocampus of Alzheimer's disease patients. And so that combination of high MUFA and high mead acid might not be the best thing. So this is mice again, and again you see the phenofibrate, so that's another PPAR-alpha activator. And what's interesting about this, this is SEA, they just put the T in to mean stearic. And what happens is SEA actually goes down. So you activate PPAR-alpha, and it is lowering SEA. And that might simply be because over time, you upregulate SCD1 and you're converting that stearic acid to oleic acid. But again, you see OEA and things that activate PPAR-alpha sort of being at odds with SEA. And that's one of the reasons I find the SEA interesting, because that is the one that has presumably declined over time. In response to PPAR-alpha activation, you see an increase in PEA, you see an increase in OEA, and both of these things, of course, activate PPAR-alpha. And so you see this positive feedback loop here of activate PPAR-alpha, make more OEA, activate PPAR-alpha, make more OEA. You also see maybe a threefold increase in something called 2AG. And so that is another endogenous cannabinoid. And so this thing absolutely triggers the cannabinoid receptor and is associated with obesity. And so even though AEA drops a little bit, 2AG is there to take up the slack. And so when you activate PPAR-alpha, you have cannabinoids rising, and you have PPAR-alpha activators rising. This is part of that positive feedback loop again. So this is SCD1. When SCD1 activity is high, you make a lot of oleic acid. Oleic acid actually directly binds to and inhibits, that's what this paper shows, FAAH, which is the thing that breaks down those ethanolamides, right? And so you see AEA increases in response to SCD1 activity in this particular experiment. These are all things contributing to this kind of positive feedback loop. So I said OEA on the top, but I could have said any number of PPAR activators. I could have said oxidized fryer oil. That activates PPAR-alpha. That upregulates SCD1 and D6D. D6D directly and probably SCD1 indirectly, which upregulates oleic acid. The oleic acid blocks the FAAH, which is the thing that would normally break down OEA and AEA. And so that winds up with increasing levels of these things and increasing activation of cannabinoid receptors, etc. So just a quick recap, these are the endocannabinoid-like molecules that include ethanolamides and also 2AG. So you have AEA and 2AG, and both of those are made of arachidonic acid, and that arachidonic acid ultimately comes from linoleic acid. Well, you can get arachidonic acid directly in your diet, or it can come from linoleic acid via the action of the enzymes D5D and D6D. And those trigger cannabinoid receptors CB1 and CB2. These are associated with obesity. You don't want these. You want these to go down. You have OEA, and that comes from oleic acid, and that's an ethanolamide. And as you've seen, it does lower appetite. It does lower inflammation. OEA can prevent obesity in mice in the lab, and it has shown a little bit of effect on weight loss in humans. And it activates PPAR-alpha, which I'm arguing is perhaps problematic, but it's complicated. And in the next video, I'm going to continue to put the idea of activating PPAR-alpha into more context. I've been taking coconut oil, as I've said in the last videos. That has a fad in it, lauric acid, which also is a activator of PPAR-alpha. It's not nearly as potent as OEA. We don't want zero PPAR-alpha, but I think taking sort of pharmaceuticals that activate it, or even OEA, which activates it a lot, is maybe of questionable benefit, right? And PEA, which is made from palmitic acid, looks a lot more like oleic acid in its activities because it also activates, it's also a pretty strong activator of PPAR-alpha. And so that kind of leaves SEA, which is made from stearic acid, on its own, because this also lowers the appetite. It also lowers inflammation. It seems to have positive effects on the D6D and the SCD enzyme systems, but it is the lone one that, as far as we know, does not activate PPAR-alpha and does not activate cannabinoid receptors. And so it stands on its own. That's why I am happy to be offering it as a supplement. I'm wondering if increased generation of SEA is one of the reasons that people see positive benefits of consuming stearic acid itself. And if this is sort of, stearic acid in pill form, time will kind of tell on that. I just got it made. I just got it in. I'm as excited to get mine as you probably are, or hopefully are, to get yours. That's it for this time, guys. I hope that's a lot of information. This is kind of a complex topic, and not enough research in this area has been done. And so I'm kind of putting this story together with limited evidence. And I'm trying to fill in the blanks, and I'm being forced to make some guesses. And a lot of the stuff we just don't know, but I think this is a very interesting product. I think doing other things to increase saturated fats and to decrease oleic acid, and of course to decrease linoleic acid and arachidonic acid in your system are all things that are going to play into this ethanolamide system, right? And so it all kind of adds up. And like I say, next time I'm going to talk more about PPAR-alpha's real role and look back at that coconut study, or that lauric acid study with the mice, and how that reversed obesity, because that's a really interesting study. So come back next week, and thank you for watching.